Let us begin. Hello, everybody. Looks like we have some people who are making good progress on the bomb, which is great. We have a lot of people who are, still making progress on the bomb, which is 100,000% fine. It looks like we have one person who has attempted to cheat, which is interesting. Let's see. I'm not sure what to say about this, but I hope that you finish the bomb, whoever you are. Any questions about the problem set? So there was something online that said you should update the grading server with your partner if you're doing it with a partner, which means that you work together, but then you have to do phase 7. So the grading server is now set up to give a place for you to enter your partner. Today, we're going to finish up our discussion of assembly, and hopefully we will get to assembly for system calls and assembly for debuggers. But let's just go ahead and get started. As usual, I have the C files. You don't. You have a couple C files, but you don't have all of them. First, we're going to look at data representation in the form of assembly. Many of you anyway, I think some of you will be relatively familiar with this, depending on how far you are in the bomb. What do you think this function is doing? Teeth! Oh, God! Yes, Megan.
The first parameter.
Is it returning the first parameter from the function? So if it was returning the first parameter of the function, that's very close. Its pointer is the first parameter of the function. Okay? So there's multiple syntaxes for dereference. And in x86 assembly syntax, when you see parentheses around a value, around a register value, that means that that register value is being dereferenced with the single exception of the LEAL instruction. Okay? So here, we are using RDI as an address. We are dereferencing that address. Okay, so RDI is the first parameter, as you know. What do you think RDI is pointing to? Anybody? Is it 1 byte big? Is it, let's see, in the back. What was your name? Peter.
8 bytes big.
8 bytes big.
I'm sorry, 4.
I'm sorry, 7. So why do you say 4?
Because it's EAX, not RAX.
Because it's moving it into EAX, and because we see the L suffix on the assembly instruction, which means moving long, which is 4 bytes in x86. Okay? If it was a Q, then it would have been an 8-byte value. So maybe this is returning star int. Well, it's returning star unsigned, but star int would have been the same. So we have a function with 1 parameter. Could have been 800 parameters, only one of which was used, where that parameter is a pointer to an unsigned. Good. 35. What about this? So the pattern is almost the same, right? We have the same sort of instruction prefix. It's another move. We have %RDI into EAX. Those are the same arguments. But this is a different move instruction rather than move L. It's move SBL. So what do you think? The L is long. The B is, everybody? Byte, yes. And the S is signed, right? So what is the type of the argument to this function? Signed char. Signed char. Does retq imply returning a quad word? And if so, why is it still used when returning a long? Because quad words for x86 are longs. They're the same thing. It's a disaster. I'm sorry. Right? C doesn't specify exactly how big a long is. It simply says that a long is bigger than an int. On a 64-bit architecture, a long is 64 bits big. x86, for backwards compatibility reasons, L long always means 32 bits. And of course, in GDB, as you've seen, if you want to print an 8-byte value, you call it a G, a giant. I mean, there's backwards compatibility reasons for all of this, and you start to understand why backwards compatibility is nobody's favorite part of designing software. Shrink this a little. Okay. F36.S. Okay, so we used to have a move Sybil, now we have a move Zibble. So the Z is probably a zebra, a 0. So this argument is probably what? Opposite of Panic in the Disco. It's an unsigned char, right? Something about this, something about that is being pointed to is likely to be an unsigned char because we're moving a 0 extended byte into a long, okay? But you've also noticed something else, which is that now we have a 2-parameter function, at least, because we're using both of the initial 2-parameter slots, RDI and RSI. If you haven't seen this syntax before, what this means is that we add these values. So this is a form of indexed addressing. A full table of all of the different kinds of indexed addressing. It's in your book. It's in the ASM 1 lecture notes. OK, so what do you think this function is returning? Yeah, Teddy?
Yeah, it's like indexing into the pointer. So like you give it a pointer and then the index you want to get from it, and then it returns like A of that, like A of I or something.
OK, so it's indexing into the pointer. You give it the pointer and an index, and it's doing A of I. Great. So how do we write A of I? Brackets. Yeah, this is just an array dereference. Every time you see this kind of addition together, you should expect there to be some relatively complicated user-defined type, either an array or a structure. Because basic types are accessible by their addresses simply. You don't need to add stuff together. So let's confirm. So we have an array of unsigned chars, and we have a long as the index, and we return A bracket X. Next one. Let's look at the difference between this one and the last one. So the minus lines were in the last function we looked at. The plus signs are in this function. So we still have a move Zibble, but the index is now RAX rather than RSI. And we have this move Slook from ESI into RAX. What's going on? Let's see, Megan. It's sign extending the index from a long to a quad. Move SLQ, sign extend from long to quad, just like move ZBL, 0 extend from byte to long. Okay? So what does that say about the type of the index argument, the second argument? Yeah, what's his name? David. We know that it's signed. For sure it's signed. The last one was also signed, although it turns out that would have made no difference. But the last type was a long. What do you think this type is? Signed long. Would we need to extend OK, I wish I should start doing different voices for the different kinds of longs, right? So like in the abstract machine, maybe we have a long. And in x86, we have a long, right? So long, which is what we had in the last one, right, was just simply added to the address. It was 8 bytes big, signed long. Yeah, Hassan. This is an int, right? So the int argument so this is actually, to me, an interesting difference between the two C files that has a significant impact on the assembly. So you wouldn't necessarily be able to tell I wouldn't have expected that difference if I hadn't set it up this way. So we just changed this argument from a long to an int. The argument is being passed in a register. The register is an 8-byte register, right? So you might have thought that it would be part of the calling convention that if you passed an int as one of the register arguments, that you would sign extend it. What we're seeing, what the compiler is telling us, is that it does not do that. What the compiler is telling us is that when an integer is passed in as an argument, that integer is only in the lower 4 bytes of the relevant register, and the upper 4 bytes might be, we don't know what they are. Okay? They might be, for example, 0. But we can read a lot just from the type, from the sizes, right? We're not really looking at sizes. We get some type information from whether a value is used as a address or not. Okay. Question: would RAX EDI be valid adding a 32-bit register to a 64-bit register? I don't actually know that. Has anybody seen RAX EDI? It looks to me like in the examples that I've put together, I have not seen that. So I'm not sure that that's valid. So the question that this person is asking is, would we ever see that R in the index argument be an E? So that we were adding an explicitly 4-byte index to a register value. I don't believe so, but I don't know for sure. Somebody could figure it out. Okay, what do we think about this? Yeah, name? Ethan.
Your first argument is a pointer to a short.
First argument is a pointer to a short. Is it an unsigned short or a short? Or, it's a signed short, because swol. Signed, word to long. I'm really going to annoy everybody. Let's take a look. Yes. Why do we add registers like this, but have other assembly instructions for add? Why do we have these complicated and interesting indexed memory addressing modes? This is all about compacting instructions into as few bytes as possible. And it is not necessarily a good idea. So the modern way of building architectures does not have all of these complicated addressing modes. Modern architectures, and this started with the DEC Alpha chip and other reduced instruction set chips, they don't have as many instruction addressing modes, memory addressing modes as the x86 does. But one benefit that the x86 style does have is that we can refer, we do get more compressed executables, which means that they load into memory faster. So we didn't talk about this 2. What's the 2? This is the scale of the index. And what this says is that rather than adding RDI and RAX, we multiply RAX times 2 and add that to RDI. So what this is telling us is that we are referencing an array of elements that are 2 bytes big. And the possible scales that we're allowed are 1, 2, 4, and 8. We don't get anything else. That's it. If you want a scale that's bigger, if you have an array of 16-byte objects, for example, you will see more arithmetic instructions to figure out, to compute the index. Right, 39. What's this? We're meant to really roll ahead. Is there a surprise on the screen? No. No. If I look at this, I think that this is an array of ints rather than an array of shorts. So last time, we'll do another diff. Last time we had a swol This time, the S and the W drop off because we're loading a 4-byte value, right? So loading a 4-byte value into a 4-byte register, no problems. We see that, as expected, we're loading that 4-byte value from an array of 4-byte values. It would be really surprising and upsetting to see a 2 here, because then you would be loading data that was in overlapping regions. That make sense to everybody? Okay, so let's look at the C code. Hooray. 40. Now we're putting things together that we've learned. So what do you guys think is going on here? So in every other dereference that we've seen that the scale of what we were loading was the same as the size of what we were loading. When we loaded a 4-byte value, the scale was 4. When we loaded a 2-byte value, the scale was 2. When we loaded a byte value, there was a B over here, the scale was 1. The scale was absent, which means scale of 1. So here, we have a scale of 4, which means that there's an array of things that are at least 4 bytes big, right? We can trace back the index, which here is RAX. We can then trace backwards and see that RAX came from ESI with sign extension, right? So that's just the second argument. So there's no extra computation on that second argument. Any integer might be passed. So we know that RAX times 4 is a multiple of 4. It's not more aligned than that. It might be 0, it might be 4, it might be 8. It will never be 3. So what is the type of the array that we're dereferencing? Yeah, what's your name?
Struct of some type.
What was your name?
Kevin.
Kevin? Yeah. Is it a struct of some type? It is. Okay, it's a struct of 4 chars. So the size of a struct of 4 chars is 4. There's no padding because each of the chars has alignment 1. You can push them right up next to one another. And we're returning the first component, right? Because the first component is located 0 bytes off of the multiplied by 4 address. Very good. If you're returning a short, why does the compiler still return through EAX? That's a great question. I think the answer is in the calling convention. The calling convention says that you always return at least 4 bytes of data. So I think even when you return a signed char, it might sign extend it out to EAX. That should be verified. OK, how about this? So you see an 8-byte scale. Does that mean that we're finally returning an array of longs? No, because we're loading a 4-byte value. So this is the same as the last struct question. Only now the struct has 2 words in it. Can I explain move SLQ again? So move SLQ. What this instruction does is it takes the value that's in ESI, which is a 4-byte value, and sign extends it. So in other words, it takes the most significant bit, bit number 31 of that 4-byte value, and it replicates it 32 times. And it loads that 32-bit value into the upper 32 bits of the resulting register. So that's a really complicated way of saying that it takes a signed 4-byte value and makes up the exact same signed 8-byte value. The signed 8-byte value with the same meaning. And then it stores that 8-byte value into RAX. So if the signed 4-byte value was -1, the signed 8-byte value will be -1. So the upper 4 bytes of RAX will either be all 0s or all 1s, never anything else. All right. Here's some schluck. You sort of know what region of class we're in, so you have some expectations that are probably correct about what this value is. What do we got here? Yeah, Avi. Am I indexing into a 16-byte array? So the scale appears to be 1, but Avi's right. We are indexing into an array of some object of 16-byte size, right? Because we multiply the index by 16. We shift it left by 4. A shift of n is the same as multiplying by 2 to the n, considered unsigned. So that's exactly what we're doing. So what's the size of the value that we're accessing? 4 bytes. Everybody, you can 4 bytes. And so what are we expecting to see? How big is the struct? The struct is 16 bytes. What does the struct have in it? 4 4-byte units. It's a pretty good guess. 4 words. We're nearing the end of this region. Okay, so what is the type being loaded? SBL. What's the type being loaded? Signed byte, signed char. What's the size of the thing? 4 bytes. What's the index that we're loading into the struct? Third. So will that be the first element, the second, the third, or the fourth? Fourth. 0 indexing. The first element of the structure would be at index 0. Okay, so we have K, L, M, and N. We return N. Our friend, LEAQ. The difference between 43 and 44 is very... Whoop. Scroll it off. Nobody can see. Okay. Well, you already saw the answer. But the only difference in instructions, we have exactly the same arguments, but we've now replaced move SBL, which loads from memory, with LEAQ, which loads the effective address. Effective. Who knows what effective means? What this does is this takes the address that would have been computed by the move instruction, but rather than dereferencing that address and loading data from it, it just uses the address. So this is a more compact way to write 4 times RAX plus RDI plus 3. Okay? So you'll see this used in place of add, and we've seen it before as well. And I already showed you the difference in the C files, but here's the difference in the C files. That corresponds to, rather than dereferencing the array, returning an address in the array. And there is, to me, something interesting going on here, which is that when you see this C syntax, it's easy to think that what's going on is something is being accessed, and then we're taking its address. That's what the syntax kind of says. But what that corresponds into instructions, there is never an access. There's no access, right? So if A was a null pointer, this will work. This will not cause a crash if A is a null pointer. It won't cause the most defined behavior, but it won't cause an immediate crash because the thing is not being dereferenced. So it's like you write more characters, but less happens. That's the interesting thing about pointers. Can I please go over LEA? Hopefully we just did. So the N in front of N, RDA, RAX adds an amount or an address. Yes, it does. But unlike the index that goes inside the parentheses, the thing that goes outside the parentheses has to be a constant. Okay, so the index inside the parentheses is always a register. The offset outside the parentheses is always a constant. It might be 3. It might be some large number, such as the address of a global variable. We've seen both of those. Great. This one is harder. I'd like some guidance. What would you like to see? Okay, you've not been able to tell the names of parameters before now, but you might be able to tell the names of the parameters to this function if you ask the right questions. So first of all, how many parameters are there? I see at least 3. Okay, we see RDI, which is the first parameter, ESI, which is the second parameter, and EDX, which is the third. I don't see any other register that is being used before it's defined. We are using RCX, but we set it to a specific value, right? So we're not reading it. Somebody just tell me to hit spacebar. Okay, thanks. Okay, what's the name of one of the parameters? Just shout it out. Someone said I. I is a pretty good guess. How about another parameter name? M. M is another pretty good guess. So what is this string? So this string is being passed, if we look back, this string is being passed to assert fail. There's another string, if we pass down further. There's that string. That string is also being passed to assert fail. You now know the name of all 3 parameters, I, J, and M. Okay? So if you remember how assertions work, what an assertion does is it computes an expression, and if that expression is false, then it exits the program, it aborts the program, and prints a message. And the message that it prints is equal to the expression, right? So it's like the expression is treated 2 ways. First of all, it's turned into a string, and second of all, it's actually evaluated. So this string, I is less than M rows, is used in this assertion, failure, the one that starts at LBB03. So where do we jump to LBB03? Right there. Okay, we will cover jumps later in the lecture. But what this is doing is the comp instruction is computing a subtraction. And then if the subtraction is less than or equal to 0, we jump to LBB03. So the assertion is asking whether I is less than M rows, M arrow rows. Where is M? Is M the first argument or the second argument? It's the first argument, because the first argument is the one that's being dereferenced. So M arrow N rows, that's a dereference. And I is the second argument. Okay, so what we know so far is that we have a function called mget that takes some pointer to something. It's a structure. We know it's a structure. And we have another argument. The second argument is I. Probably the third argument is going to be j. What do we know about the structure? We know it has some component named width and some component named height. Where's the width? Where's the height? What are their types? Yeah, name? I'm sorry. Matt.
So n rows is the first one,
N rows is the first one.
and then the columns is the second one.
Calls is the second one. And how big are both of them? 4 bytes big, because we're loading 4-byte values, right? And we can see the 4-byte offset for n calls, right? So we have some struct int n rows, int n calls. And we literally know what the first line of, and this is a pointer to that struct. We know what the first line of code here is, most likely, right? The compiler is allowed to move stuff around if it can tell it would make no difference. And we know what the second line of code is. Now, tell me what the rest of the code is. So after we do the jumps, we have 2 of these. We saw those before. What are those doing? Yeah, Rob.
Sign extending the I and J.
They're sign extending I and J. Yep. So let's take a little tabulation of what we know. I'm not going to copy all of the lines of code, but we know right now that RAX has the sign extended version of what? J, right? And we know that RCX, is that right? Yes. Has the sign extended version of I. Next. There's something more in the struct. What is that thing likely to be? Is it a flat value like an integer, or is it a pointer? It's a pointer. First of all, it's 8 bytes big. Second of all, we use it as an address. So things that we use as addresses are almost always pointers. Okay, what's interesting here, though, is it looks like there's multiple pointers going on. So what is the type pointed to? Okay, so we have one more thing in here. We don't know what its name is. There's no actual information in this file telling you the name. But if we follow this through, we can figure it out. Yeah, Teddy. It's like a 2D array. It's an int star star array. That's right. So how could you figure this out? Multiple ways. One way, as we've sort of mentioned, is going backwards. When we return, the return value is in the RAX register. That value is a 4-byte big integer. It might be a 4-byte big something else, but whatever it is 4-byte big. So we assume it's an integer. We obtain that integer by dereferencing a pointer that's in RCX. We obtain RCX by dereferencing a pointer that's in RDX. We obtain RDX from the structure. So there's one layer of pointer in the structure, then there's another layer of pointer underneath that, and then we find an integer. So what is the return statement? Two layers of indexing. The first layer of indexing, we use RCX, which is I. So this value m arrow a, has type int star star. When we add one array dereference, we take off one of the stars. This value, m arrow a bracket I, is int star. And then the last argument, the last array index is rax, which is j. Okay? Very good. Seriously. Okay, how about this one? Yeah, Meg.
I had a question about the way scaling factors are 8 and 4. Does that tell us something about the type of array?
Does that, so we're indexing into the array, and the scaling factors are 8 and 4. Does that tell us something about the way the array is laid out? It does. So we can tell also from the way the data is used, right? We can tell what data, whether data is a pointer or we can tell. I have to be careful here. If data is used as an address, then it is a pointer, unless you're working with something that is not really C.
The 8 is, and it is
Because it's a pointer, it's 8 bytes big. Right? 64-bit architecture, always 8 bytes big. Pointers are 8 bytes big. Okay, 2 questions. What does n? Okay, so if we leave off this value, what does that mean? Well, that's like a multiply and an add. If you leave off the base, it's counted as 0. If you leave off the index, it's counted as 0. If you leave off the scale, it's counted as 1. If you leave off the offset, it's counted as 0. So you'll never see that syntax, n parenthesis, comma, register n. That you'll only see in an LEA, at least in my experience, because that's not a very good pointer. There are very few times that you multiply like a pointer by 4 and you get something that's useful. Why does this push RAX but pop it into RCX? Okay, that's a great question. We talked about this a little bit last time. Anybody remember from last time? Yeah, I'm sorry. Name? David. It has to do with padding. We're aligning the stack to a multiple of 16 bytes. So when we push RAX at the beginning, that's garbage. We don't know what RAX contains, and it doesn't matter. So why are we pushing RAX in this function? But why are we aligning the stack? Most of the functions that we've looked at are as simple as this, but they don't have any pushes or pops in it. The reason is that we might call a function from this function. We might call underscore underscore assert fail. Okay? So the compiler could have further optimized this. And if it knew more things about assert fail, it might optimize this. So for instance, we know that assert fail never returns. So since assert fail never returns, it would be safe to blow away the current function stack frame. You could jump to assert fail rather than call assert fail. That would be safe. But the compiler doesn't appear to know that or hasn't taken advantage of it. Yes, sorry, name? George.
So why does it pop it into RCX?
Why does it pop it into RCX? Why doesn't it pop it into RAX?
Oh, RAX is already filled for the return.
RAX is filled for the return value. It's got to get rid of it somehow, right? Part of the calling convention is that you leave the stack you leave the stack pointer exactly as you found it. You're allowed to modify the stuff with smaller addresses. But when the function returns, right before the return instruction, the stack pointer has to be exactly where it was when the function started. Okay? So this is doing a pop into RCX just as a way to just to shift the stack pointer back to its original value. This value that was in RAX is garbage. The value that's in RCX is garbage. RCX is a caller saved variable which means that this function mget has no responsibility for what's in it when the function returns, right? You would never see pop q into rbx because you would never see that, sorry. You would not see a garbage value loaded into rbx right before a return because rbx is a callee saved register, which means that it is part of the calling convention that rbx, when a function returns, has to have precisely the same value that it had when the function began. Okay? So that's, most registers are caller saved. If the caller wants to remember a register's value, the caller has to save that value and then load it back when the function returns. rbx is not. rbp is not. rsp is not. Our 12 through 15, I think, are callees saved. Okay. Going back to this. So we have an evocative name for this function, second plus third. How many arguments? One argument, right. At least one argument, but only one argument that we've used. Is that argument a pointer or not? It's a pointer, totally. It's totally a pointer. So what do you think we're doing here? Yeah, name? Juan. Adding the second and third nodes of a linked list. Totally. That's exactly what we're doing. So we take a linked list, we go to the second node in the linked list, load its integer value, then go to the third node in the linked list and add its integer value. Going back to the assembly, the first line gets a pointer to the second node in the linked list. The way the linked list is arranged, the pointer to the next element is located 8 bytes into the struct. That's what that 8 is. The second line goes from the second node to the third node. So now our CX has the second node and our AX has the third. The third line dereferences RAX and puts the result into EAX. So that overwrites the third pointer, right? Which is OK, because we're not using the third pointer again. And then we add the value in the second node by dereferencing our CX. And we can tell that that's a 4-byte value because of the L. And then that's what we return. Awesome. Why do we pop the trash value into RCX? Why not have an instruction that pops it to nowhere? This is a good question, but in practice, it's extremely likely that an instruction that popped it into nowhere would be no cheaper. What you do see is if you have like 30 values to pop, the compiler will never say pop RCX, pop RCX, pop RCX, pop RCX 30 times. Instead, it will simply add 30 times 8, 240, to the stack pointer. Okay? In the same way that when the compiler starts a function, it subtracts that amount from the stack pointer to reserve space. Why pop it all? Why not just subtract and add? Smaller instructions. Is it just a convention that RDI is first, then ESI and EDX? Yes, that is the calling convention. Cool, great, break. Then, fun, awesome. Okay. Let's do some jumps and some conditional moves. What's this doing? I'll just show you what it's doing. So if b equals x, return a. Otherwise, return B. So in general, in assembly, when an instruction executes, we just go on to the next instruction. The exceptions are loops and branching control flow, where the program has a choice to make. Either it does one thing or it does another thing. Here, we're making the choice if B is equal to X. So how that turns into assembly is kind of interesting. It uses the flags and condition codes registers. So here's what we do. First, we move B into EAX. And what's interesting about EAX, of course, is that EAX is the return register. So since it's the return register, when we move something into it, we might very well return that thing. We then perform the comparison between X and EAX. Now what that comparison is doing is that computes a subtraction and then throws away the result. But it remembers a couple of facts about the result. It remembers whether the result was equal or greater or less or signed. So this comparison computes B minus X. Because subtraction, the way all of these instructions work that have two arguments, there's a source and then a source plus destination. And the computation is source destination equals source destination operation source. Okay, so we flip them around. So this is computing B minus X. Then J and E, jump if not equal. So what do we return if B is not equal to X? I hear X, B. Anybody for A? Well, we jump over A. Did we ever load X into a register? No, because the comparison doesn't actually load X into a register. The comparison doesn't affect any registers except for the flags register. So if B is not equal to X, we return B. Otherwise, what do we return? A, which is what we saw. How about this one?
X equals 0, return B, else return A.
If X equals 0, return B, else return A. Yes. You said if X equals 0, return B, else return A. The code says if X is not equal to 0, return A, else return B. The compiler is free to organize these branches however it wants. There are ways even to influence the compiler to say, put this value closer, this branch closer. So doesn't n paren reg mean deref reg plus n? That is correct. We're back to using, notice that this is what we call instruction pointer relative addressing, which is a form of addressing that is used to refer to globals. Okay? So these are not arguments. These functions have no arguments. They just are globals. They just operate on globals. The RIP register is the instruction pointer. It is the address of the currently executing function. And yes. OK, how about this one? How many arguments does this function have? There's some weird stuff going on here. We'll get through it together. One argument. Anybody know what test does? So test and comp are similar instructions so that they're only used to set flags. Yes, in the back. What's your name? Ed.
Performs an add and discards the result?
It does not perform an add. It performs an and. So it's x and x. Okay? Now these move instructions do not affect the flags. So the move instructions just leave the flags alone. So this test sets the flags. We then have two move instructions. So we load the address of B into EAX, and we load the address of A into ECX. Somewhat interesting that those are 4-byte pointers. It's because the compiler knows that they're going to be loaded into globals. Compilers, man. Then, this line. So this is called a conditional move. And the conditional move is like an assignment, but it only performs the assignment if a condition is true. So it's like an if condition, then do assignment, compressed into one instruction. So what this assignment is doing is it is saying, if EDI is 0, then move RAX into RCX. Okay? So I'll write that down. So C move EQ of R1 into R2 has the exact same effect as this. JE, that's the E part, to L, I'll just make up some numbers, L2. In L2, we do move Q R1 into R2, and then jump back to L1, where L1 is right after the JE. Okay? A more compressed way to say this would be to switch the jump condition, make that a JNE. Question, Enrique? Okay.
So I agree it's only one parameter, but why are you using the ECX register, which is the 4th parameter register?
Because there's no 4th parameter, so we can use it. Why are we using the 4th parameter register for something that's not a parameter? Well, when a function begins, if there is a parameter, then its value is in ECX or RCX. If there is no parameter, or you don't use the 4th parameter, you can modify RCX and use it however you want. This is the same as, like, you can use RAX for a purpose that is not returning a value. It becomes the return register when the function returns. Okay? So the meaning of a register in the calling convention is only part of what makes that register useful. A lot of the time, we just use the register as scratch space. And that's what this register is being used as. Okay, so finally, we dereference the value that we got before and return that. Question, Will?
How do you know that A and B were pointers as opposed to, like, I would guess they're integers.
I know that A and B are pointers because they are dereferenced. But A is not a pointer. A is a global variable, right? So the correct thing to say, let me rephrase your question so that I can give it the answer yes. How did I know that A and B were names of global variables? You know, because A and B are treated as addresses here. I'll show you the C code. So this is the exact same C code as we had before. Almost. Before we had a global X, and then we had much easier to understand branch. Now we have a local X, And the compiler has decided that the better thing to do with a local x is a conditional move. So why do compilers prefer conditional moves? It turns out that branches are some of the more expensive things that a processor can do. The most expensive thing that a processor can do is make a mistake. So if you take a null dereference, that takes the processor forever to recover from. It's just like, oh my goodness, it sort of runs around the house, puts all of the like fallen, crockery back on the shelves, gets everything organized, and then starts the debugger. The next most expensive thing you can do is dereference memory. Memory is very slow. We've talked about that before. We'll talk about it again. After that, though, taking a branch, taking a conditional branch. Because essentially what a conditional branch does is it's like it forks the universe. The processor, in order to make progress as fast as possible, it's always trying to work ahead of the actual instruction pointer. It's always trying to make progress beyond the current instruction. When the world branches, when a condition might be true or false, the instruction pointer effectively branches. And modern processors actually try and make progress on both of those branches. It's only when it figures out what the condition is that it sort of like stops and throws away the world that doesn't exist to concentrate on the world that does. The conditional move is like a branch, but it's a much more local and targeted branch. So the world that forks is just one register. This is a much faster version of this branch. Okay, how about this? Any guesses? How many arguments? I hear 2. That's what I count. What are the arguments? How many bytes? Someone is going like this, which is correct. 4. What's the name of this function? If I were to give this function a real name rather than f, what would you call it? I would call this function max. What we're doing is we're computing EDI minus ESI, just for the sake of the flags. If EDI is greater than or equal to ESI, we move EDI into ESI. Then we move ESI into EAX. So when this function returns, EAX contains the greater of EDI and ESI. Great. Okay. We have some more of this, but I think in our remaining time, what question, Megan? So the question was, in the C code, if we look at the C code, we see if A is greater than B, return A, otherwise return B. In the assembly, we see a greater than or equal to test. If A is, well, it's actually if B is greater than or equal to A, right? Because no, RDI is the first argument, right? So this is if A is greater than or equal to B. So the question was, why did the compiler change a greater than or equal to into a greater than? Well, does it matter if this is a greater than or equal to or a greater than? No, it doesn't. Because if the values are equal, then you can move or not. Doesn't matter, they're the same. So the compiler, in its infinite wisdom, has noticed that equal things are equal, and it just substituted whatever one it wanted to use. Questions? Yes?
Why would it prefer the greater than or equal to? Because then you may do an extra move when you could just not move it.
What was your name?
David.
David. So why would it do a greater than or equal to? I think the intuition that you want to have here is not that a move is more expensive than a not move. You want to, the purpose, you get to use a conditional move instruction like this when basically both branches are effectively the same. The expensive thing in a branch is figuring out whether or not to take the branch. Here, both of the values are loaded into registers. Assigning one register to another is as free as things get. So there really is no practical difference. That's my intuition. It's also the compiler's intuition. Teddy. Oh, also, one more thing. The compiler has no idea how often equal value this function is passed equal values, right? It might be that this function is never ever called with equal values, in which case, who cares? It might be that this function is always called with a being greater than b. You would need, there is a way that compilers can use profile information about what actually happens when a program runs many, many times to optimize its code generation. But this compiler has no such information, so it doesn't know. Teddy.
Would ternary operators just compile down to this?
Do ternary operators compile down to this? Yeah, they do. Unless, if a ternary operator has a bunch of function calls and garbage in it, then no. Okay, we have a question. Why does test-L EDI trigger cmoveq only if 0? Isn't EDI equal to EDI? Yes, it is true that EDI is equal to EDI. And comp-L EDI would always return 0. And so the equal branch would always be taken. But test-L EDI is EDI bitwise and EDI. And the result of that bitwise and is 0 if and only if EDI is 0. OK. Where does branch prediction happen? In architecture class. I want to show you two things in our remaining time. First, if there's any additional questions on how assembly works, now's the time to ask. But I would like to show you roughly how debuggers work, and I would like to show you roughly how system calls work. OK. You might remember our add program. It knows how to add numbers. It was what we looked at on the first day of class. You might remember as well the actual instruction bytes that implement add. It's up there at the top. The instructions that are used to implement add by this compiler are 8D0437C3. So the first 3 bytes are an LEA, and the 4th byte is C3, which is return. Now, if you're anything like me, you can use a debugger for a long time before you stop to ask yourself, what is going on? How does the debugger know to stop at a particular place? How is this interaction working? Let's take a look. If I run this add program outside the debugger, let me show you the program. But it actually is printing 1 + 2 = 3. But before that, it prints some bytes. And these are the bytes that it prints. So it starts at the address of the add function and then just prints the next 4 bytes. Let's go back to our debugger. I'm going to run the code a couple times. OK, now I'm going to set a breakpoint on the add function, and we'll run it more and more time. What do you see? This is different now. This is not what it used to be. Our add function is 8D0437C3. Our add function now is CC0437C3. Let's take a look and just make sure that this is really what's going on. wait a minute. When the debugger starts, the values of those bytes have gone back to being 8D04737C3. So it's like the instructions are changing dynamically. That's exactly what's happening. This is how a breakpoint works. When you set a breakpoint in a debugger, what the debugger does is, before the program runs, it overwrites that instruction in the instruction stream with a special instruction that means give control back to the debugger. Then when the debugger resumes, it goes and undoes its work because it doesn't want you to think that anything has changed. So we only get to see the changed instructions if we print them from within the program running. When we're examining data with the debugger, when we're examining instructions with the debugger, we're examining the real program, not the instrumented program. For me, this is magical. So this is one of the advantages, massive air quotes. But this is one of the advantages of a complex instruction set architecture. There is an instruction that is 1 byte long that is enough to give the debugger control. That instruction is called int3, and its hex value is cc. And if I run my program one more time, you'll see that that is, in fact, the value that's been overwritten over the add function's first instruction. Okay, question? Yes, Juan.
For some weird reason used its own instructions in computing, does that mean that using a debugger could cause weird behavior?
Sorry, ask the question one more time.
If, like, for some reason a program were using its own instructions.
If a program was using its own instructions, for instance, if it verified that it was not running under a debugger by checking out breakpoints, yes, that would change. We could make this program get very confused if it relied on the byte values of its instructions. Make sense? Yeah, Will. Does this mean that GDB is allowed to write to the text block? That's exactly what it means. So you may have noticed if you've tried to run GDB ever on your Mac, that the first time you try to run it, it says, I don't know how to do this. And then a little window pops up, and Mac OS says, you're trying to get around what Steve Jobs wanted. Are you sure? Type your password. GDB is using special privileged operating system interfaces to gain control over other programs that are running. In fact, a debugger, once that hoop has been jumped through, a debugger that I run is able to connect to and completely destroy the memory of any other program that I am running. You can attach to a running program, stop it, overwrite all of its memory, and then start it up again and just see what happens. I can do that to Emacs if I want. I don't want to. I kind of do want to. But it would just crash. Maybe we'll do that later. OK. So you might ask now, what is this int3 instruction? What is that? Seems like a strange instruction. Well, let's back out one more level, and instead of talking about debuggers, we'll talk about something more general, which is printing stuff. Say I want to print a message to the screen. What kind of instructions would you use to do that? This is like a trick question, but it's like one of these questions that when I think to ask the question, I'm like, wait a minute, really, what instructions would there? I mean, would you have a print instruction? Would that print instruction work for PostScript printers? I mean, how would it work? We don't have specific instructions for printing. What we do have are instructions for calling out to the operating system. We have instructions that essentially give control from the currently running program to whatever the operating system is underneath. So you could imagine that instead of special instructions, you would link together with the operating system so that your program and the operating system were in the same address space, and you could just make a function call to the operating system. That would be so incredibly unsafe, it would be a disaster. That would essentially give every program permission to destroy the entire disk, for example. And a major task of the operating system is to protect programs from each other and from their own worst instincts. So if a program has a null pointer dereference, we want that program to crash. We don't want the whole operating system to crash. There are special instructions that allow us to talk to the operating system. Okay, maybe you remember this. You remember this very cute child. And you might remember that if we try and execute an add function that's located 72 bytes into her, we get a very nasty message. So what program can I use to figure out how those messages are being printed? Anybody remember? strace, right? So if I run strace on this program, I'm getting the messages, but interspersed with two system calls, write and nanosleep, write and nanosleep, write and nanosleep. So where write is the system call that prints this message to the standard output, and nanosleep is sleeping for 250 million nanoseconds, which is how we sleep for a quarter of a second. Let's see if we can't figure out how those system calls are implemented. So what we're going to do is I'm going to load up my add-in code. Let's take a breakpoint right there. We'll set a breakpoint there right before the add function is called. So this is before we call add, right? But after we've loaded Hello Kitty into memory. So I'm going to run GDB on add-in. I'm going to set a breakpoint at addin.c line 62. And I'm going to run with my cat and the 72 argument. OK. Our breakpoint is set. Let's figure out what address is going to be called. It's been optimized out. What we can do is we can figure out that address using what we know about the values. So this is the address 72 bytes in to the add.jpg. Let's set a breakpoint there. I think I might, let's see, set a breakpoint, add a register. There we go. All right, we're just going to single step it instead. So I'm single stepping, I'm single stepping, I'm single stepping. Now I'm at the relevant address. I'm now executing code inside of add. So what GCC was telling me here, what GDB was telling me is, I can't debug this thing that's not even code, right? Because it was loaded into memory at a non-code in a way that's different from the way code is loaded. I probably could have figured out how to do that, but we're not going to bother. So we're going to print a whole bunch of instructions starting at that address. Do you guys see anything sort of that might be relevant? Syscall. There's an instruction called syscall. Where do you think the arguments are for that system call? Let me scroll just a bit down. Okay, which of these is nanosleep and which of these is write? If you remember the S trace, we saw alternating write, nanosleep, write, nanosleep, write, nanosleep. So probably the first one is write and the second one is nanosleep. Do you get any confirmation of that? Well, write took one argument that was standard out file descriptor number. Standard out file descriptor number is 1. Where do you see 1? I see 1 there. I also see 1 there. It turns out that the system call calling convention for x86 is as follows. On Linux, the system call number is loaded into the EAX register. Then the first argument is loaded into the RDI register, just like before. The second argument is loaded into the RSI register. The third argument is loaded into the RDX register. Any of that like ring a bell? Sounds like the normal calling convention, and it almost is. The fourth through sixth arguments are passed in registers, I believe, R10, R9, and then R8. Why? I don't know. Let me show you the evil code. And we're going to look at a lot more code like this. Do I not have the evil code? There we go. So this, my friends, is how you call a system call. So what you are seeing here is this is happening in the C library underneath you. Every time you call printf, some version of this code is eventually running. But you don't need to you don't need to use the system printf. You can write your own and just call a system call by dumping the correct instruction into the instruction stream. What this asm function does is it says, hey compiler, stop compiling C for just a minute. Instead, just put this instruction in. Okay? You could put anything there. You can put RDI and RSI and addl. You can do whatever you want. What this is saying is, hey compiler, this variable, this local variable arg0, don't put it on the stack. Put it in this register. Put this argument in this register. Put this argument in this register. And then what this says is, hey compiler, make sure that all of those arguments have the values they're supposed to have. And then what this says is, hey compiler, when that system call instruction completes, the result is going to be in RAX. Okay, we have just gone way lower than most people do. It's very fun. Enjoy the rest of your problem set.